Let's follow two experts as they use StressDiffVis. StressDiffVis includes two views, the tree view and the comparison view. In the first case, the expert aimed to optimize the structure of a wooden chair. 1,300 Newton vertical and 450 Newton horizontal forces were applied to the seat and backrest, respectively. The expert began by importing the base model, Model A. Using stress-aware volume visualization in the tree view, the expert quickly identified areas of high stress at the backrest and chair leg ends, appearing yellow and opaque, and areas of low stress at the seat, appearing blue and transparent. This led to a focus on reinforcing the backrest and legs. To reduce stress on the backrest, the expert added two armrests, creating Model AO. However, the extent of the improvement was still hard to recognize. Using difference-aware volume visualization, the expert selected Model A as the reference and computed its difference with Model AO. In the resulting visualization, the blue regions indicated stress improvement, while the red regions indicated stress deterioration compared to the reference. An extensive blue region appeared along the lower backrest and both ends of the lower rail, showing the armrest significantly improved structural performance. Next, the expert focused on improving the chair legs. Two alternatives were introduced, Model AB, with stretchers connecting the front and back legs, and Model AC, with stretchers connecting the left and right legs. The precise effect of the additional stretchers remained unclear in the tree view. So, the expert compared each model to Model A, using difference-aware visualization. In Model AB, blue regions appeared around the hinges and feet, indicating stress improvement, exactly where Model A had high stress. There was a slight increase in stress in the middle of the legs, suggesting that the stretchers effectively redistributed the load, improving overall structural integrity. On the other hand, Model AC showed very little difference. This was because the front-back stretchers in Model AB effectively resisted horizontal loads. As a result, Model AC was discarded. Models AO and AB effectively improved the backrest and the legs, respectively. However, in comparison view, distinct kinds of segments were observed. In these segments, the voxels showed increased stress in Model AB but only minimal changes in Model AO. The expert selected these four segments as a segment group, activated it, and filtered its voxels in the tree view. These segments were mostly in the middle of the legs. In another segment, Model AO caused deterioration. The back legs appeared red in Model AO but blue in Model AB, showing that the armrests introduced additional stress where previously improved by Model AB. To address these trade-offs, the expert developed Model ABO, which combined both the armrests and front-back stretchers. Through difference-aware visualization, the expert confirmed stress improvements in both the backrest and the legs. Although stress slightly increased in the middle of the legs, this region initially experienced low stress, so the deterioration was considered acceptable. Ultimately, the expert successfully optimized the chair's structure using StressDiffVis. In the second scenario, the expert focused on the structural improvement of a truss bridge model. The base model was labeled AB sharp C sharp E sharp D sharp. Here, letter A represented the skeleton of the truss bridge. B, C, E, and D referred to the support members, while the sharp symbol indicated thickened supports. Firstly, the expert designed three alternatives, Model A, B, C, E, D, where all supports were thinned, Model AB sharp D sharp, where diagonal supports were removed, and Model AC sharp E sharp, where vertical supports were removed. In the stress-aware visualization of Model ABCED, the expert observed distinct yellow regions in the diagonal supports, indicating high stress concentration. In the other two alternatives, no clear stress concentration patterns were observed. To examine stress differences, the expert employed difference-aware visualization using the base model as a reference. In Model ABCED, diagonal supports had higher stress than vertical ones, confirming their role in bearing horizontal shear. In Model AB sharp D sharp, stress shifted to the vertical supports and lower beam, indicating a weakened structure. In AC sharp E sharp, stress also increased in the lower beam. To more clearly analyze vertical and diagonal supports, the expert turned to the comparison view. First, the expert segmented the alternatives based on stress distribution and ranked segments by their variance. Segments corresponding to the vertical supports were highlighted. Although stress increases in Model AB sharp D sharp, it remained within a safe range, indicated by green color. Next, the expert ranked segments by stress magnitude. The expert identified segments with high stress in the diagonal supports, which appeared yellow only in Model ABCED. Based on this, Model ABCED was discarded, while the other two models were kept. The expert explored further material reductions by removing supports at the bridge ends. This resulted in models AB sharp and AC sharp. However, it was hard to see stress changes in the tree view, so the expert analyzed the segments instead. The expert observed increased stress in models AB sharp and AC sharp, especially at the connection of the supports and the upper chord beam. This was especially concerning, as connections were fatigue-prone parts. Given the elevated stress at these critical joints, the expert decided against further reduction and finalized models AB sharp D sharp and AC#, E# for testing under different loads.